Hello. Today we're going to talk about pendulums, which is the other very common example of simple harmonic motion, aside from masses and springs on the AP exam. So let's take a look at a pendulum. Pendulum goes back and forth because at all points except for the bottom, it's got a net torque on it. And this net torque causes it to rotate. So if we think back to our grade 12 equilibrium class, or just the rotational unit, net torque is equal to the perpendicular component of your force compared to a radius to your pivot times your distance to that pivot that the force is exerted on. So if we want to find the perpendicular component of our force, we can draw a little triangle, which will resemble very strongly our triangles from inclined planes. And you find out that the force that is perpendicular to our radius to our pivot, this force component is perpendicular to that. That is mg sine theta, and our distance from our pivot that the force is applied is L, the length of the rope. So think through that a bit. Convince yourself that this is the perpendicular force, just like in a standard torque question, and that this is your distance from your pivot. Now, if we're starting from this formula, torque net is just like F net equals ma. Torque net is I fish, or moment of inertia times angular acceleration. So that makes sense. And we're just saying that the perpendicular component of our force is mg sine theta. We'll throw a little negative in front of it because that's showing that the torque is in the opposite direction to our angular displacement. And our distance from our pivot is L. So that kind of makes sense. Our I is not too hard to figure out because pendulum is basically a point mass if we ignore the mass of the rope, which is mr squared for moment of inertia, r being the length of the rope in this case. So we replace I with ml squared, and then angular acceleration is just the second derivative with time of our angle. And now it's starting to look a little more familiar with this second derivative, hopefully. We can cancel a bunch of stuff out. Cancel out one of our L's, cancel out our M's. And then we do something kind of sneaky. One thing I'd like you to try is take out your calculator and just put it in radian mode and try for small angles, find like sine of 0.1 or sine of 0.2 or something like that. You'll find out that it's effectively sine of 0.1 is 0.1 and sine of 0.2 is 0.2. So as long as you've got a small angle, you can use this thing called the small angle approximation, where sine theta is just basically equal to theta as long as your pendulum isn't swinging too crazily. So if it's just little swings, you can make this replacement. So we can replace sine theta with just theta because at small angles, they're roughly the same. Just kind of a neat trick. Do totally use your calculator until it makes sense to you. Now, once we move everything over to the other side and replace sine theta with theta, it looks like this, which should look very, very much like what we had with masses and springs. Instead of x, we have theta. Instead of k, we have g. And instead of m, we have L. Again, we will do the same thing as before. Like, the second derivative is equal to the original times some junk, but negative. That sounds kind of like a sine thing to me. Sine or cosine. Anyway, as soon as this pops up, you'd be able to see we're replacing theta with a sine omega t, or angular velocity times t. If we start at the equilibrium position with some velocity, or our theta is equal to the amplitude, our max theta times cos of the angular velocity times t. We're making that assumption because it fits our situation where our second derivative is equal to negative some constants times our original. So if we go and do that, we're like, hey, the second derivative of theta, assuming that it's a sine omega t, you'd have 2 omegas, two angular velocities coming out due to the chain rule as you take two derivatives. And derivative of sine is cos, and the derivative of cos is negative sine, so that's where we get the negative. We can cancel out the negatives and the a sine omega t, and we're like, hey, our angular velocity squared is g over L, or our angular velocity is the square root of g over L. And doing the exact same tricks as last time, we can be like, hey, well, angular velocity is defined as 2 pi over period, which again, you can think of it as angular displacement divided by time. For one full cycle, you've got a 2 pi displacement, and period is the time for that to happen. So anyway, we can rearrange, solve for t. Our period, 2 pi over the angular velocity is period, which is 2 pi over root g over L. And that just kind of flips the root g over L to L over g. And this is a formula you should have in your data pages and where it comes from. Keep in mind, frequency is just 1 over period. And so we can just do 1 over our formula for period. And just everything gets flipped. 2 pi becomes 1 over 2 pi. Root L over G becomes flipped, so it's root G over L. And that's a formula for your frequency. I don't believe you get it, but you do get the formula for period, and you can just flip everything, and you get your formula for frequency. Again, we can do our tricks to figure out our max angular displacement, our max angular velocity, and our max angular acceleration. So our A is defined as our max angular displacement, which makes sense because the sine theta, the biggest that can get is 1. 1 times A is A. So the biggest angular displacement you're ever going to get is A. So you can just replace that with your max amplitude of angular displacement. And then if you take the derivative, you end up with some cosine function, which is has a max value of 1, and then it's going to be multiplied by this junk, your max angular displacement times root g over L. So that will give you the max angular velocity. And by exactly the same logic, if you think it through, hey, sine has a max value of 1, multiply it by this junk, that means angular acceleration has a max value of the max angular displacement times g over L. So keep these guys in mind. They're occasionally useful and not too hard to figure out once you believe this original formula for angular displacement. You just take a couple derivatives and use a little logic. One more thing quick. Notice that none of our formulas for angular velocity, period, or frequency, they do not depend on the mass of the pendulum at all. If you ever go in a swing, you will find that no matter how heavy you are, you will still go back and forth at the same rate. It is not affected by the mass of the pendulum. It is very much affected by the acceleration of gravity where you're at and the length of the pendulum. The length of the pendulum is usually how you adjust the frequency, period, or angular velocity of a pendulum. And that's it for pendulums. Thanks for listening.